Okay, so first things first, the powers. Do we know what powers are? A power looks like this. Two to the power of 5, right? 2 to the power of 5. Yes. If you guys don't know, a lot of students at this, when they see this towards the beginning, they think it's just 2 times 5, right? Which is not the case. It is 2 times 2 times 2 times 2. Basically, it's the 2 multiplied by itself 5 times. That's what powers mean. That's what powers are. Very quick, just a little note. This is 2 to the power of 2, yes. But there's a little nickname to it. What is it called? 2 squared. Right? There's another one. This has a little nickname to it. No. 2 is the squared. Anything to the power of 2 is squared. No. Who here knows the nickname? Cube. 2 to the power of 3, aka 2 cubed. And does anyone know the nickname to 2 to the power of 4? Huh? Cuatro. No, it's not cuatro. That's Spanish for 4. There is none. It's just 2 to the power of 4. And then 2 to the power of 5, and then 2 to the power of 6. Is there? There probably is in some place. Okay, so that's all. That's the basis of the powers, right? But guess what? There are some rules with powers. There are some full-fledged rules that you all must remember. Do we know what this is right here? Eight. So the first rule is anything to the power of 1 is that same number, right? That's an actual rule. It's important that you guys note that. There's another one. Let's see this one. 6 to the power of 0. We have a 0, we have a 6. We have a nothing, which is 0. Anything to the power of 0, this is a rule, anything to the power of 0, my friends, is, come on, 1. Anything to the power of 0 is 1. Yeah. And I'm pretty sure, yes. No, we're just going over the lecture right now. Do you need paper or anything? Okay. Yeah, anything to the power of 0 is 1. Now, I'm pretty sure you guys are tempted, really, really tempted, to be like, why? Don't spiral down that. Don't ask why. There's a very, very good explanation to it, but all you need to know is one thing and one thing only. Anything to the power of 0 will always be 1. I'll do you one better. $1 million to the power of 0. You know what it is? It's 1. It's 1. So that's a very, very important note to take home with you. Now, what? You guys just want to get under my skin. Did I just hear why? Oh, so don't worry about that just yet. Like I said, you do not want to ask why. Don't ask why. Because it's a long answer. I'll explain it to you guys, but we have to get through some of this stuff first. because it's a long day today. But I'll explain it to you guys just for fun later on in a couple years. So another rule. Here's a good example. 4 to the power of negative 2. What's that? Did I hear 16? Somewhat there. 1 over 16. So that's what I'm going to explain to you right now. Your guys' facial expressions are just like really hysterical. So here's the rule. Anything to the power of a negative number is, well, I can't really finish off the sentence. I have to explain it to you. So let me show you how this is. 4 to the power of negative 2. Anything to the power of a negative number is that exact same operation over 1. So this is what I mean. All this becomes is this. 1 over 4 over 2. Whenever you have a negative, the 4 and the 2, it's still there, but in order to get rid of the negative, you must put it as a fraction form as the denominator of 1, over 1. Or under 1, sorry, the denominator, so under 1. That goes for anything. 5 to the power of negative 6. All it is 1 over 5 to the power of 6. It's 1 over whatever it is that's given. But now, why is it that 4 over 2 became 1 over 16? Well, all we did was finish off the problem, right? What's 4 squared? It's 4 times 4. What is 4 times 4? 1 over 16. Let's finish this one off. What is 5 to the power of 6? What's 5 times 5 times 5 times 5? I'm just going to whip this out very quick. Oh my God. I shouldn't have picked such a big number. It is 1 over, let's see if I have space here. $15,625. Big number. I know, I should have. Should have, could have, would have. So, all you guys got to note is that anything to the power of a negative number is 1 over that number to the power of the other number. These are rules. These are rules, rules, and rules.
What if it was a negative number?
Oh, yeah.
Tanny. So, what if there's a negative number, such as, let's stick with something smaller, like how about negative 2, right? To the power of, what do we want, negative 3? One recording. 1 to the power of negative 2 thirds, right? Right?
What's the negative 3?
No, it's negative 2 to the power of negative 3. And chances are, you guys, you are going to see this. Whenever we're dealing with negatives, it's usually identified with the parentheses, right? So, bring that along. It's the same thing. Now you just have to ask yourself, what is negative 2 multiplied by itself 3 times? So think of it like this. What's negative 2? I'm kind of jumping the gun here. I was going to explain negatives, but someone decided to ask a question, so now I have to answer it. What's negative 2 times negative 2? There's no need for those dots. What's my problem today? What's negative 2 times negative 2 times negative 2? Well, let's do this one first. What is negative 2 times negative 2? If we remember yesterday, do the operation. What's 2 times 2? 4. And then ask yourself about the rules from yesterday. What's a negative times a negative? Positive. So guess what? The answer is 4. So now you just ask yourself, what's 4 times negative 2? This one right there. Well, do the operation again. What's 4 times 2? 8. What is a positive times a negative?
Negative 8.
The answer is negative 8, right? So all the answer is 1 over a negative 8. It's the same thing. Anything to the power of a negative is just 1 over whatever the answer is. Cool? So now, quick little review in a blank.
We got a quick question on that.
Yeah.
So, parentheses means multiplication.
Yes, it does.
It means negative. You just threw me off. You said that's a negative and you put it in parentheses, but that just means multiplication.
Yeah. Well, no, what means a negative is the negative sign,
Okay.
right? Parentheses are usually used for multiple things. It's used, A, to identify multiplication, right? If something in a parentheses is next to something else in a parentheses, it means multiplication. With no operation in the middle, it means multiplication, right? But parentheses are also used to as a label. It's mostly used to identify a negative also. So if you have a 2 minus a negative 3, that looks too weird. So what they've done is they're pretty much saying, yo, I'm a negative inside here, right? So it could be as in
Oh, shit.
as a,
I did 2 minus 3 and I would multiply that. I would say, yeah, do that. Oh, gosh.
no, if you notice, if you notice, look here. If there was no sign there, no operation, this is straight up multiplication, right?
Straight up.
Straight up, right? But because we have an actual operation, subtraction is the thing here. The parentheses, all it's doing here is labeling the negative. It's just separating the negative from the operation. Cool. So very quick, anything to the power of 1 is what? Anything to the power of a negative number is what?
1 over.
1 over the whatever, right? Anything to the, on your guys' quiz, if you guys put that, 1 to the whatever, I'll probably like give you bonus points for that just for making me laugh. Anything to the power of 0 is what? 1. 1 for some reason. If you put that in the quiz also, I'll give you bonus points. 1 for some reason. Those were it. Those were powers, right? And I just went over the negative power, or negative numbers to the power of whatever it is. Just treat it the way I just did it, right? Negative 2 to the power of 4. Just treat it like this. You're actually getting that negative number and you're multiplying it by itself 4 times. Okay? Cool. Then comes the next lesson of the day. Roots. Who here knows what a root is? Who here knows what a root is? Your hair? The root of your hair? No. It's this sign right here. The square root. This is the cousin of the power. Seriously, they are very closely related. What is 3 squared? 9, right? Here, it's backwards. We're working backwards. All they're asking is, in this problem right here, they're asking what number multiplied by itself 2 times equals 9. 3. It's kind of a backwards approach, but it's a pretty simple approach. But there is something you guys got to note. It's the famous perfect squares. Who here has heard about the perfect squares? This is what the perfect squares are. What's 1 times 1? What's 2 times 2? What's 3 times 3? 4 times 4. Oops, that's 16. What's 5 times 5? Now I'm going to stop there. We are going to continue on, trust me. But there is all these right here that you're looking at as the final answer. Those are perfect squares. There's an infinite amount of perfect squares because there are an infinite amount of numbers, right? But there's only a select few that we usually use. Why? Because it only gets to it's good for you to remember the perfect squares up to 12 or 15, right? For instance, this should continue on to 6 times 6. 6 times 6 equals what? And then 7 times 7, and then 8 times 8. You should do that all the way up to what 15 times 15 is. Why? Because that helps you out with a lot of problems in math, in more advanced math, right? And it helps you just to look good. When someone says, hey, what's 8 times 8? You should be like, oh, 64, right? It's one of those things that you should like be on top of, right? But what are perfect squares? What are perfect squares? Perfect squares are these right there, all the answers right there, which means, for an example, what is the square root of 36? 6. That's why it's helpful to memorize all these perfect squares, is because if you're given something like this, you shouldn't have to take out the calculator. You shouldn't have to do anything. You should be, what times what creates 25? 5, right? Those are perfect squares. Why? Because they come out as a whole number. If you're given this, what is the square root of 7? Does anyone know what the square root of 7 is? I don't know at the top of my head. You know why? It's because it's a long decimal number. Those are not perfect squares. Perfect squares are the ones that dish out whole numbers for us. So luckily for you, for those of you taking your GED, for those of you taking my quiz, for those of you that want to do good in whatever math class, unless they provide calculators, you won't be asked questions like these. Why? Because it's too long of a decimal number. Geniuses could do these, right? People are going for their masters in mathematics, and even then they could only do it for probably the square root of 10 or something, but anything more they can't, you got to have a calculator for it. You need to actually take out a calculator and be, what's the square root of 7? Oh, it's 2.645751311. That number times itself twice creates a perfect 7. We don't have to deal with that. What we deal with are the perfect squares. What we deal with are all of those that are right there and a little bit more. So we start, what is 7 times 7? What is 8 times 8? What is 9 times 9? What is 10 times 10? Now here's when people say like, okay, you could just memorize up to 10. You could. But do yourself a little favor. Memorize a little extra, up to 12, up to 13, 14, 15, whatever. Try to remember all the perfect squares at least up to 15. 11 times 11? 12 times 12. Now, 13 times 13. I've just memorized it up to like 10. 13 times 13, what's that? I gotta get this out. I should memorize this. 169. Okay, whatever. You guys get the idea. Go learn it up to 12, 13, 14, 15. But just note the most important thing is those are the perfect squares. So when you're given something like this, what is the square root of 121? That quick. Because there's only so very few, well, there's an infinite amount of perfect squares, but there's only a select few that we usually deal with on a daily basis. Simple, right? Pretty simple. Jeez Louise. So now we're going on to the next thing of how numbers could be written as. Because that's all we're doing today is we're looking at these rules. We're looking at how things work and whatnot. All in preparation for next week once we enter algebra. That's right. We're close to algebra. Yeah. Pre-algebra, but still algebra, right? But this is all in preparation for that. But that's why yesterday all we did was go over positive and negatives, integers. And today we're just going over this. And that's why the quiz is just going over all of this, all in preparation for next week. So we're trying to work our minds to how to operate with numbers, how numbers are written, how numbers could be solved and seen. And the next one is a famous one. It is the scientific notation. Who here knows what the scientific notation is? It looks something like this. There's two ways it is. There's two ways it could be seen. Give an example. Okay, you're the boss. (6.2) times 10 to the power of 5. Right? So, don't worry about it just now. Let's just see what we're looking at. This, my friend, is scientific notation. Why do we have a thing called scientific notation? Well, believe it or not, numbers do get pretty big. They get pretty long. And guess what? Sometimes the beautiful calculator, or sometimes your business's database where you're inputting numbers only allows a certain amount of space, right? So what they did was, if you have a long number, you could rewrite it like this, and it will still represent that same big number. So pretty much this is another way to write a big number. But now, what is the big number? Just looking at this, well, how would you solve, what would this scientific notation equal to? Well, to know that, you just have to know how to solve scientific notations. And it's pretty simple. Pretty simple. Do you see this little decimal point right there, 6.2? Do you see how the 10 is to the power of a positive 5? All you got to do is get this 6.2, go to the decimal, and guess what? All you got to do is move it 1, 2, 3, 4, 5. Add the zeros, and guess what? It's 620,000. Not too big of a number, but trust me, they could get pretty big.
Is it always times 10?
Yep, that's the beauty of the scientific notation. We're going to do some more examples. But pretty much, you move wherever the decimal place is here, whatever amount it's telling you to move, in the direction that it's telling you to go. In this case, this is a positive 5, which means I must go that way 5 times from the decimal point. If, my friends, you were given, oops, 6.2 times 10 to the power of negative 5. Guess what? Same thing, but a little different. You no longer go that way. You got to go this way. 6.2. You start wherever the decimal is. You go 1, 2, 3, 4, 5. My final answer is 3, 4, 5. 0.000062. It's important to take note of that direction, right? I'm throwing a lot at you guys, mostly for the fact that we don't have class tomorrow. That was a little punch in the face by the college. We were supposed to do this tomorrow. We were supposed to do this separately tomorrow. But I have faith in you guys. Faith that you guys can do this. You guys can do this. Review these videos that I'm posting up. Look at the front of the worksheet. See, work your mind with it. No one has done this before. Not even you. No one ever in the existence. You guys are the first human beings in the world to do this. Okay, one last example like this. And then I got to teach you one last thing. It's still scientific notation. But how about if we get 4.4 times 10 to the power of 8. Again, you guys, this is how scientific notation is always going to look like. So all you got to note is it positive or negative, the power? It's positive. That's important because now you know you're going to go that way. So it's 4.4, 1, 2, 3, 4, 5, 6, 7, 8. That's where the decimal goes. Final answer being, geez Louise, 440 million. Yeah, you're right. 440 million. Do you see how scientific notation is helpful? Do you see how helpful it is?
So what you're saying, that's the answer?
That's the answer.
We don't need to do anything else with the 10 and the 8? That's what you did.
No, that is what you did. If you literally put in your...
I'm waiting for you to finish it. I'm like, oh, it's not what we were...
No, that's the answer. 440 million. All we're doing is converting from a scientific notation to standard notation. By the way, this is called standard notation, the way we always write numbers, right? Maybe that's hey, you know what? Write that down, you guys. I might have to throw that on a quiz. What? I'll find a way to rephrase the question, but whatever. That's standard notation. That's scientific notation, right? And just for fun, if you were to do on the calculator 4.4 times 10 to the power of 8, it'll come out the same thing. Your calculator might not fit it, but fine. It's the correct answer. But now, what if? Actually, before I continue on, let me show you one last example of the one we just did. 4 to the power of 10, 5. I just made this up. I don't know if it's going to come out good. So sometimes you might be given whole numbers, right? Sometimes. Where's the decimal in this 4? It's still behind the 4, so that's where you're going to start. 1, 2, 3, 4, 5, right? So 400,000. We got that? I just had to throw that out there. Okay, so now, but now. So now, what if you're given, my friends, what's a good example that we have here? What if we're actually given what if we're given a number? What if we're given a number? 89 million, right? We're given a standard, we're asked, convert from standard form to scientific notation. So now we're working backwards. How do we write this in scientific notation? Counting is key, right? You start wherever the decimal is. Where's the decimal? It's always at the end of any whole number that's given. It's always at the end, right? It's invisible, but guess what? It's right there. And what we do, this is going to be key, you count how many steps it takes to get right behind the first whole number.
Can we do
Yeah. Let's do this one first, and then we'll do another example just like that. So what I mean by that is this. You move it 1, 2, 3, 4, 5, 6, 7. That's where it should go. Right behind the first whole number. Yeah. Oh, did you think of that one? I could see that. Yeah. So whatever you want to think of it, behind the first whole number, which is that one, or in front of that one, or behind. I don't know how what you need to say so that you could have it in your head, but just make sure it's always behind whatever that is.
I think if we count until, like we count all after 0, it will be easier than we move to the other number than 0.
Like?
Like you just count until behind number 9. Yeah, it's easier.
The way the scientific notation, so this answer right here, how is it written as scientific notation? It's written like this. How much did we move it by?
7.
Was it 7?
Yes.
Okay. Is that right there?
But it couldn't be 89 times 10 to the 6.
No.
Yeah.
No,
Why not?
because that's not how it works.
But it's an answer.
It is, but that's not scientific notation.
In 7 places, why would you do 6?
Yeah.
If we put it like
Then the
It says
decimal
behind
would be
them.
after the 9.
because you have 6 zeros, so you can put 6 right away. You don't need to put more.
I know 100% what you're thinking. I know 100%. But the decimal point must always be behind the first whole number. It must. It's a rule. Computers have it mixed into their algorithms. Calculators have it in their algorithms. This is how scientific notation is displayed. This is the way it's displayed. What?
But technically, if you did
Yes, you're right.
89
I know where you're going.
times 6, you'd get the same answer.
Yeah. Yeah.
Okay.
Yep. But don't have that in your head.
Okay.
It must always go behind the first one. Yes. Thank you. A+. And yes, even if there was more numbers such as this, 4, 3, 2, 1.
Ooh, 4, 3, 2, 1.
Like that. Same rule applies. Right? Where's the decimal? It's right there. It's right there. So you go 1, 2, 3, 4, 5, 6, 7. Wow, 7 again, whatever. But the scientific notation is 4.321 times 10 to the power of 7. Yeah, I should have. Is the way scientific notation is, Nanny. I'm sorry. I'm just really sorry. I wish I could make it easier, but that's just not how math is. So again, what if, my friends, I'll do something smaller, but same thing. Yeah. Yeah, right? So we're given a standard notation. We're just given a decimal number, that's all. You count. You count, you count, you count. But this time, we got to make sure to put our negative. So here we go, 1, 2, 3. 3. 3. Behind the first whole number that you come across. 3.82 times 10 to what? Negative 3. Did I finally bring Danny down? Did I finally stump you?
Not yet.
So, I already know what's going to happen. It's going to be confusion in your guys' head. You guys are going to be like, oh crap, does it go in behind or in front, this and that? Does the decimal go that direction or this direction? What the heck, what the heck, what the heck? Through practice, you guys are going to easily nail down scientific notation. It's all about directioning. It's all about counting. And as long as you have in your head, this is just another way of writing big numbers. Then you could be more at ease. It's going to be easy. It's going to be simpler. Because it's a decimal number. So if we notice here before, this was a whole number, right? It was 43 million, right? Here it's 0.00382. So yes, that's a good note to take. Why do we go negative here? Is because it's a decimal number. It's 0.00382. Yeah. After I answer some more questions. But as for the recording, we are done. Good luck, YouTube.